Hey, everybody, let's continue on 11.3 for calculus. 11.3 is on dot product. Here we're looking at decomposing vectors into orthogonal components. Now, we've done this in a previous section. When we did 3, -2, we wrote this as 3i plus -2j or 3i minus 2j. I hat and j hat are orthogonal vectors. They meet at 90 degrees. So we are used to separating or decomposing vectors into a sum of orthogonal vectors with I, j, and k, but we don't have to stick with the Cartesian coordinate vectors. We can use any set of orthogonal vectors, not just vectors along the unit or along the axes. So let's take a look at doing that with an example, or a general picture, not an example yet. If I got vector W1 and vector W2, we can come up with vectors along those, E1 and E2. So W1 is K1 times E1, W2 is K2 times E2. Right now, I don't have E1 and E2 listed as unit vectors because this still applies. So we would do, and if this is V is the sum of the two vectors, W1 and W2, we're going to have K1 E1 plus K2 E2, which is the norm of V times the cosine of theta times that E1, plus the norm of V times sine of theta times E2. So there's like the trig components. Before I introduced the E1, E2, we could have said it was like that. E1, E2 is putting in a multiplier for it. And having vectors along those. Now let's take a look at what happens when we do that. Dot product can help us find out what E1 and E2 are kind of easily. So check this out. If I take V and dot it with E1, I've got E1 times K1 E1 plus K2 E2. So we've got, remember E1 and E2, the way we've defined them, E1 and E2 are orthogonal. So the dot product when we distribute E1 times E2 is 0. When I do E1 times E1, E1 dot E1, I should say, the dot product of those two, that was the norm of E1 squared. But I wrote them both out here. E1 dots into that just fine, but E1 dot E2 is 0. And if we make E1 and E2 unit vectors, then what happens? E1 dotted with V is just K1 because the magnitude of E1 squared is 1. And so this zeroes out. This is 1. We're just left with K1. We do the same thing with E2. E2 is going to zero out the E1 component, leave us with the norm of E2 squared, and that's just going to give us K2. So E1 dotted with V and E2 dotted with V are just scalars, K1 and K2. This is kind of like hard to picture what I'm saying. We're going to do an example with numbers in a second, so bear with me. So another way of writing W1 is, we had W1 is K1 E1, and I can rewrite it as E1 dot V times E1, and I can write W2 as E2 dot V dot times the norm of E2, if we're using unit vectors for E1 and E2. So let's take a look at the next part of it. Let's do some practice work, see how this works. let's do an example where we express V, the vector V is 3, 4 as a sum of vectors, one being parallel to the vector B, 4, 2, and then a vector orthogonal to B. Now remember, a parallel vector can't overlap the same vector. So let's just find the unit vector along B. And then we'll find the orthogonal vector from that. So let's just walk through our steps of what we're doing. I got a picture here. I drew it. V is there, B is there, theta is the angle between them. The goal is to find how we sum it up, B and K2 and E2. So let's find K2 and E2 and we can do it. Notice if I subtract here, if I subtract the B vector over, I've got K2, E2 is equal to V minus B. So keep that in mind. And we're going down to it. Okay, step one, let's write B as K1, E1 to find E1. So let's normalize B. E1, we want it to be a unit vector along B. So to find a unit vector along B, we divide B by its magnitude. That's what we're doing here. So if we do that, we've got 4/2 divided by the norm of 4/2, 4 squared and 2 squared is 20. Square root is that. So we've got 4 over root 20, 2 over root 20. E1 is 2 over root 5, and then 1 over root 5 are the components. And that's effectively like that. That's our E1 right there. Okay. Now we want to find K2, and from our formula from the previous page, K2 was the magnitude of V sine theta. K1 was magnitude of V cosine theta. We can find both. We can express V as K1 E1 and K2 E2. So let's find sine theta and cosine theta to find our K1s and K2s. We're going to use our E1 to do that. So cosine theta, well, not really, but finding the K1 and K2, we'll use it. Cosine theta, if we want to find the angle, we got to do the dot product of our two vectors divided by the magnitude of both vectors. So cosine theta is our vector 3, 4 dotted with 4, 2 divided by the norm of both. 3 times 4 is 12. 4 times 2 is 8. So 12 plus 8 gives us 20 on the top. The denominator, the norm of V is 3 squared plus 4 squared is 5. So that's handy. We'll write that down here. Norm of V is 5. So we've got, and we already did norm of B. It was 20 up here. Let's not do it again. So we've got 12 plus 8 is 20. Square root of 25 is 5. The 20 is 4 times 5. I factored out the 2. I ended up getting 10 root 5 on bottom or in the denominator. So cosine theta is 2 over root 5. So I don't want to find that in terms of radians or degrees. I just drew a picture. Cosine theta is adjacent over hypotenuse. So I can find sine theta by doing, or we can find y by doing Pythagorean formula. 2 squared plus y squared equals square root of 5 squared. You're going to find out that y equals 1. And so what do we do with that? Sine theta is opposite over hypotenuse, 1 over root 5. And recall K2 is the norm of V times sine theta. K2 is V times sine theta. 5 times 1 over root 5 is root 5. So that's our K2. And I found K1 real quick. It's V, the norm of V times cosine theta. And that was 2 root 5. So now that we're done with that, we've got K2, we've got K1, we've got E1. All we need is E2. And we can use that first thing that we had wrote up above. K2, E2 is V minus B, which is 3, 4 minus 4, 2. So K2, E2 is negative 1 over 2. Divide by K2, we get E2. And K2 was square root of 5. So the unit vector E2 is -1 over root 5, comma 2 over root 5. Now we've got our K1, our K2, our E1, our E2. We can write B as a sum of orthogonal vectors that are not our IJK vectors. That was the decomposition of them. Doing the -1, -2 like that was pretty easy. All we had to do was the B minus B to find it. But turning them into unit vectors, we did this. So these equal that. And you could check that. You could multiply 2 root 5 into this, and you'll see the root 5s cancel. 2 times 2 is 4. The root 5s cancel here. 2 times 1 is 2. Same thing here. Root 5 knocks out the denominators. We get -1 over root 2 on both of them. And that'll bring you an end to this section of our dot product section, 11.3. We got more to do. Peace.